Hi students, I am Sheeba, EC department from Emmanuel Arthur JJ College of Engineering. Today we are learn about the topic CMOS devices. CMOS means complementary metal oxide semiconductor devices. CMOS devices means it is the integrated circuits that use pairs of p-type and n-type semiconductor field effect transistor. That is, it use two MOSFETs. They form the backbone of modern digital electronics, including microprocessors, memory chips, and image sensors, due to their very low static power consumption and high noise immunity. Next, the diagram of CMOS devices. It consists of N channel and P channel. The N channel and P channels are diffused to P-type substrate. It has three terminals. First one gate, second one source, third one drain. Next, the figure shows a IC chip of CMOS devices. Next, the working principle of CMOS devices. First one, complementary pair. It uses both NMOS and PMOS transistors working together. Second one, switching action. When an input changes, one transistor turns on while the other turns off. Low power usage. Power is only consumed during state transitions, drawing near zero power when idle. Next, the key features and benefits of CMOS devices. First one, high noise immunity, less prone to electrical interference and false switching status. Second one, high packing density. Small footprint allows millions to billions of transistors on a single chip. Third one, wide voltage range. It operates efficiently across various power supply levels. Next is the applications of CMOS devices. First one, microprocessors and microcontrollers, core processing units in computers and smartphones. Second one, memory devices. It is the fast, reliable data storage such as SRAM, image sensors, digital camera and phone sensors that convert light into electronic signals. Fourth one, analog and mixed signal, data converters and radio frequency communication circuits. Next is MOSFET transistor characteristic under static and dynamic conditions. MOSFET characteristics describe how the transistor behaves under steady DC conditions versus changing or switching signals. Static traits define DC operating regions, while dynamic traits deal with internal capacitance, switching speeds, and transient power loss. The three regions of MOSFET is: first one, cutoff region. It occurs when the gate source voltage is less than the threshold voltage. No channel forms and the drain current is zero. It acts like an open switch. Next one is linear region. Linear region is otherwise called triode region. It occurs when VGS greater than VTH, that is, gate source voltage is greater than threshold voltage and the drain source voltage less than VGS minus VTH. In this channel, the channel is fully formed. The MOSFET becomes like a voltage controlled resistor in this region. Third one, saturation region. It occurs when VGS greater than VTH and VDS, VDS is equal to VGS minus VTH. In this, the channel pinches off at the drain end. The current levels off and becomes independent of VDS. It acts like a constant current source. Next is the critical static parameters. First one, threshold voltage. It is the minimum gate voltage needed to turn the transistor on. Second one, on resistance. The total resistance between drain and source during full condition. Third one, static trans condition. It is the ratio of change in drain current to the change in gate voltage. Next is MOSFET under dynamic conditions. Dynamic conditions dictate how fast a MOSFET can switch and how much power it loses during transitions. Under AC or high frequency switching, a MOSFET cannot change states instantly due to internal parasitic capacitance. The role of parasitic capacitance is the physical structure of a MOSFET creates internal capacitance that must charge or discharge during every switching cycle. Next is input capacitance. It is composed of gate to source and gate to drain capacitance. It dictates how much current the gate driver must supply to turn the device on. Next one, output capacitance. It is composed of drain to source and gate to drain capacitance. It affects the energy losses when switching. Fourth one, reverse transfer capacitance. It is also known as the Miller capacitance. It creates a temporary voltage flux during switching, slowing down the turn on and turn off transitions. Next is the switching timeline. First one, turn on delay. The time required to charge up to the threshold voltage. Second one, rise time. The time it takes for the drain current to rise from its initial leakage level to its maximum value. Third one, turn off delay. The time required for the gate voltage to discharge down to the point where the channel begins to close. Fourth one, fall time. The time it takes for the drain current to drop back down to zero. Next is technology scaling. When a MOSFET undergoes technology scaling, both static properties and the dynamic parasitic capacitance you selected change significantly. Next is the impact of scaling on parasitic capacitance. When scaling down by a factor of lambda, that physical parameters shift as follows. Gate oxide thickness shrinks to 1 by lambda. Next is the dynamic performance. The dynamic performance, the input capacitance decreases, the gate driver requires less total gate charge to switch the transistor. This results in faster switching speeds, lower dynamic power consumption. Next one, secondary scaling effects. While scaling makes the device inherently faster with lower dynamic capacitance, it introduces severe static and reliability trade-offs at smaller nodes. First one, short channel effects. As channel length becomes incredibly small, the drain voltage begins to control the channel instead of just the gate. This leads to drain-induced barrier. Next, increased static leakage. Thinner gate oxides allow electrons to tunnel through quantum mechanically, causing massive gate oxide leakage current. Subthreshold leakage also increases, meaning the MOSFET never fully turns off under static conditions. Next is fringing capacitance. While the ideal parallel plate capacitance shrinks, the fringing fields between the closely backed gate, source and drain contacts do not scale down nicely. At sub 10 nanometer nodes, parasitic interconnect and fringing capacitance can dominate over the ideal gate capacitance. Next is how the industry solved scaling limits. First, to keep reducing capacitance without letting static leakage destroy the chip, the semiconductor industry shifted away from traditional planar MOSFETs to advanced 3D structures. Next is FinFETs. Fin field effect transistor. It wrapping the gate around three sides of a raised channel to regain electrostatics control. Next is GAA-FETs or nanosheet. It wrapping the gate completely around the channel for the ultimate mitigation of short channel effects. Next is power consumption. To calculate or optimize power consumption in digital circuits or power electronics, we analyze the sum of two major contributors. First one, static power. Second one, dynamic power. First one, dynamic power consumption. Dynamic power is consumed only when the MOSFET is switching states, that is from 0 to 1 or 1 to 0. It consists of two components. First one, capacitive switching power. This is the energy spent charging and discharging the internal parasitic capacitance. Second one, short circuit power. During a brief moment in the switching transition, both the PMOS and NMOS transistors in a CMOS gate are partially turned on. Next one, static power consumption. Static power is the energy consumed when the circuit is completely idle. Ideal means it is the same conditions. In an ideal MOSFET, static power is 0. Subthreshold leakages occur in static power consumption. This can be avoided by gate oxide tunneling. So finally, we can conclude the section. So thank you.